CSP Algorithms with Manuel Alejandro Umaña Rodriguez, Dahyna Martínez Pérez, Jean-Luis Pérez-DEJESUS, and Christopher Hans Mayens Matías. This is the agenda for this report. Purpose of experiment. Understand constraint satisfaction problems to develop a goal state. Study the effectiveness of backtracking search, min conflicts, consistency 3, and forward checking algorithms to identify the optimal solution for the zebra puzzle. Evaluate AI performance across different measurements such as solution status, execution time, and number of steps taken to solve the problem. Key questions and hypotheses. Can an AI agent using consistency 3 perform effectively in a constraint satisfaction problem? Hypothesis. The consistency 3 algorithm, combined with backtracking search, will have the best overall performance due to its consistency, enforcing capabilities, and robustness in constraint satisfaction scenarios.
Concepts. The experimental concepts used were the platform, which was Python programming language of a high level. The subjects were the zebra puzzle, backtracking algorithm, min conflicts algorithm, AC3 with backtracking, and forward checking algorithm. The zebra puzzle solver was a digital logic puzzle solver using CSP techniques like backtracking, min conflicts, AC3 with backtracking, and forward check. Solutions are visualized with a GUI showing house attributes and highlighting the zebra and water locations. Measure. Performance is being evaluated by checking if a valid solution is found, and efficiency by measuring execution time and steps taken. These metrics highlight the strengths of each CSP algorithm.
Experiment setup. Tools and resources utilized. The following tools and resources were used: the IMA code repository, where the initial code was found, algorithms used to solve the puzzle, backtracking search, a depth-first search algorithm that incrementally builds solutions and backtracks when a constraint is violated, minimum conflicts heuristic. A local search algorithm starts with a complete but possible invalid assignment and iteratively minimizes the conflicts by changing the variable values. AC3 with backtracking. A combination of the AC3 algorithm, which enforces arc consistency by reducing variable domains and backtracking to find consistent solutions. Forward checking. An enhanced backtracking method that looks ahead by proving the domain of unassigned variables with a new variable is assigned, preventing future conflicts. Method for comparing the performance indicated where the algorithm successful found the solution to the zebra puzzle. Efficiency measures the number of steps taken and the time required by each algorithm to solve the puzzle when a solution is found. Methods for graph creation. Data was collected by running each CSP algorithm once to solve the zebra puzzle. The graph compares the performance of each algorithm based on the time taken and the number of steps required to reach a solution. If no solution was found, it shows the number of steps completed before the algorithm stopped. Information. Here we see the solutions for the different algorithms, the first one being the backtracking algorithm, the AC3 with backtracking algorithm and the solution, forward checking and backtracking algorithm. For here we see the summary of the different information for all the algorithms utilized. As we can see, the different min conflicts ended in failure with a worst time and the worst steps. A graphical representation of the solution found, showcasing the difference and the difficulty of finding a solution, with the maximum steps taken being by a solution of backtracking.
Conclusions. CSP algorithm performance. Different CSP algorithms vary in how effectively they solve structured, constraint-heavy problems like the zebra puzzle. Each method balances completeness, efficiency, and simplicity in distinct ways, revealing the strengths and trade-offs of approaches such as backtracking, forward checking, arc consistency, and min conflicts. Efficiency of AC3 with backtracking. Backtracking with AC3 offers a highly effective solution by significantly reducing the search space early on. This approach outperforms both standard backtracking and forward checking in terms of speed and consistency, requiring fewer recursive steps to reach a valid solution. Limitations of min conflicts. The min conflicts algorithm struggles with tightly constrained problems due to its reliance on random restarts and local adjustments. Its performance is inconsistent and sensitive to initial conditions, making it less suitable for structured puzzles with complex interdependent constraints. References.